Imagine traveling 124 light-years away, through the void of the constellation Leo, to a world that shouldn't even exist by our old rules of astronomy. For decades, we've looked for little green men or radio signals, but the real breakthrough might not be a visual sighting, but a smell. Scientists thought they found a definitive sign of life on a massive ocean world, only to have the data pull the rug out from under them. Today, we are decoding the mystery of K2-18b and the impossible atmosphere captured by the James Webb Space Telescope. Welcome to SciNova. I'm your host, and today we're talking about cosmic chemistry. When we talk about finding life in the universe, we aren't talking about finding a city with lights on. We are talking about sniffing the air. The James Webb Space Telescope, or JWST, isn't just a camera. It's the most sophisticated chemical sensor ever built. It looks at light passing through distant atmospheres to see what molecules are dancing in the dark. And recently, it found something that sent the astrobiology community into a total frenzy. Let's talk about the target, K2-18b. This isn't your typical rocky Earth-like planet, nor is it a gas giant like Jupiter. It sits in a strange middle ground, often called a super-Earth. But the real excitement comes from its classification as a potential Hycean world. This term is a mashup of hydrogen and ocean. The theory suggests these worlds have thick, hydrogen-rich atmospheres covering vast, global liquid water oceans. It's a type of planet we never thought could support life, yet here we are, staring right at one. So, what exactly did JWST find in that thick hydrogen soup? The telescope detected carbon-bearing molecules. Now, carbon is the backbone of life as we know it. Finding carbon in the atmosphere of K2-18b was a massive win, suggesting that the chemical building blocks for complex organic chemistry are present. It confirmed that this planet isn't just a dead rock. It has a complex, chemically active atmosphere that is interacting with whatever lies beneath that hydrogen shroud. But then, the headline that broke the internet arrived: dimethyl sulfide, or DMS. On Earth, DMS is a very specific molecule. It is primarily produced by life, specifically phytoplankton in our oceans. When you smell the ocean on a summer day, you are often smelling DMS. If JWST detected DMS on K2-18b, it would be the smoking gun. It wouldn't just be life-friendly conditions. It would be a direct chemical signature of biological processes happening in an alien ocean. However, science is rarely as easy as a headline. When the initial reports came out, the statistical significance of the DMS detection was quite low. We are talking about a significance of roughly 1 to 2.4 sigma. In the world of physics and astronomy, that is the equivalent of seeing a shadow in the woods and being 60% sure it's a bear, but 40% sure it's just a bush. It was a tentative hint, a whisper, not a shout. It was enough to get everyone excited, but not enough to claim a discovery. This brings us to the current state of the mystery. In recent follow-up studies, the hype has been significantly tempered. New analysis and more rigorous constraints on the data have suggested that there might be no conclusive evidence for DMS at all. The signal we thought was life might just be noise, or perhaps a different, non-biological molecule that looks similar to DMS under our current models. It's a sobering reminder of how difficult it is to perform space smelling from 124 light-years away. Why is this so hard? Think about the scale. -18t is over 100 light-years away. We aren't looking at the planet. We are looking at the light that barely survives its journey through the vacuum of space. When that light passes through the planet's atmosphere, the gases absorb specific wavelengths. JWST catches those missing pieces of the rainbow. But when the atmosphere is thick and the signal is faint, distinguishing between life and geology becomes a mathematical nightmare. Even without the DMS, The existence of the Hycean model is a game changer. For a long time, we thought the habitable zone was a very narrow strip where planets had to be just like Earth, rocky and with a nitrogen-oxygen atmosphere. But K2-18b proves that the rules are being rewritten. If Hycean worlds are common, then the number of potentially habitable planets in our galaxy just increased by orders of magnitude. We are looking at a whole new category of living worlds. The search for life is moving from where are they to what are they breathing. This shift in strategy is why JWST is so vital. We are looking for chemical disequilibrium, situations where gases exist together that shouldn't, unless something like life is constantly pumping them into the air. K2-18b is our primary laboratory for this. Even if it turns out to be a false positive, the lessons we learn about how to detect DMS and other biosignatures will be the blueprint for the next decade of discovery. So, where does that leave us? Is K2-18b an ocean world teeming with alien life? Or just a massive chemically complex ball of hydrogen and gas? As of right now, the jury is still out. The impossible part isn't just the planet itself, but our own ability to understand it. We are standing on the threshold of a new era of astronomy where we don't just see the stars, we understand their breath. The truth is still out there, hidden in the light. The journey to find life is a marathon, not a sprint. Every failed detection like the DMS on K2-18b is actually a step forward. It refines our tools, sharpens our math, and prepares us for the moment when the signal is no longer a 2 sigma whisper, but a 5 sigma roar. When that happens, we won't just be talking about space smells. We'll be talking about neighbors. Thanks for watching SciNova. If you want to stay on the cutting edge of the cosmos, hit that subscribe button and ring the bell. Keep looking up.